So, next talk, or now I'm giving it, is about the computer science behind the modern distributed data store. And it is a hard problem. And what I would like to tell you today is like the 4 or 5 major challenges that we face when we create a distributed database, which we at ArangoDB, that's the company I work for, are building right now, and which is out there. So most of this is already done. And I would just like to talk about it and how computer science helped us implementing all this stuff. So the toughest challenges that I've selected for this talk is, first of all, resilience and consensus, sorting, log-structured merge trees, which is a super important topic for us. Then we have hybrid logical clocks. And finally, how can we do this full ACID thing that you know from the single server relational world in a distributed environment, distributed ACID transactions. The bottom line of this talk is you need computer science to implement a modern data store. So you can try with try and error, but most likely you won't succeed. So, yes, please? Okay, I can try to speak a bit louder. So I thought it would be on the microphone, but I guess the microphone is only for recording, right? Yeah. Okay, then I will just speak louder. Okay, thanks. So the format will always be I have a problem that I'm going to describe, and then I will show you how we can use computer science to solve it. The first problem, resilience and consensus. So a modern data store is distributed. So the data is too large for a single machine. We want to add more machines. We want to have read scaling, write scaling, and all this weird stuff. So the data store is distributed. Because it needs to scale out, thing that I was talking about, and it has to be resilient. So no matter what happens, the system should be there. If a machine is on fire, the system should be there. It has to be resilient. And this has the challenge that different parts of the system need to agree on certain things. So if you say, I'm storing a new document, and the database says, yes, I store it, and you ask for the same document again, you don't want the database to say, oh, which document? I don't know about it. It should be there. So the servers need to agree that it is there. And consensus is the art to really achieve this as well as possible in software only. And consensus is relatively easy as long as everything is good. So you have networks, you have your machines running, and they can communicate to each other. Then it's super simple, actually. But it's super hard if, no, wrong button, the network has outages, or the network has dropped, delayed, or even sent the message twice, or even more times. If disks fail and come back with old or corrupted data, if machines fail and come back with old or corrupted data, or even if your entire data center or a complete rack is down and comes back with corrupted data. And yeah, you might argue, okay, on my laptop this never really happens in my lifetime, but if you are running on a large scale, one of these events most likely will happen each night. And I'm pretty sure no one of you wants to wake up in the middle of the night to fix this. So you want the server to just work. And we even have not talked about malicious attacks from enemies. A solution to this problem are several consensus protocols. Traditionally, so the first protocol is called Paxos, written in 1998. Paxos is super good, but it's a challenge to understand, and even more of a challenge to implement it correctly. So I personally have read this paper like 5 times, and I'm still not sure if I understood everything, but the thing is super complicated. And for Raft, various variants exist to make it a bit simpler to implement and to follow. And the most well-known one is called Raft from 2013. And this has been designed to be understandable and implementable. It is still complicated, but it's doable. So my advice is, if you're interested in this topic, first try to understand Paxos. Read it a couple of times. So for some time, try to understand it, but do not try to implement it. That's most of the time a waste of time. And after you understood Paxos, or kind of understood it, enjoy the beauty of Raft and see how simple it gets. If you start with Raft, you still think, oh, it's too complicated. But this way actually works. But my advice, do not implement it either, because it's still too complicated. So you should use, if possible by any means, some of the battle-tested implementations that you trust. So there are a couple out there. Let's say Zookeeper, then we have etcd, and in ArangoDB we have also a Raft version, which is called the ArangoDB agency, and I think there are a couple of more. I think Neo4j uses Zookeeper, right?
No, Raft.
Oh, Raft implemented as well? Okay, nice. But most importantly, do not try to implement your own algorithm. Unless you have 2 years where you can freeze time, implement this algorithm, and then continue where you are. But otherwise, probably would lose a lot of time just inventing the whole thing. And now I try to do a really hard thing, try to explain Raft in a single slide. First of all, we need an odd number of servers. Why they are odd, we'll come to in a minute. Each of them keep a persisted log of events. So they just write down this event happens, that event happens in one order. Everything is replicated to everybody. So that means each of the odd servers has the same log and has to have the same log. Then they democratically elect the leader with an absolute majority. That's why we need an odd number of servers, because then one of them will have the majority in a network split. So we cut the network into half, then one half will have the majority of servers, the other half will not have the majority of servers. So they can elect the leader. And only the leader may append to this log. So you can only write on one leader, and this makes sure it is persisted everywhere. And an append only counts and is successful if a majority of all others have persisted and confirmed it. And these two rules actually allow to shut down any of these machines at any time and still have a correct state and a consistent state across all the others. Then you need a very smart logic to ensure there's a unique leader and automatic recovery from failure. I think I could give a full hour talk just only about this smart logic. So let's say we need a smart logic to have these things guaranteed. It's all a lot of fun to get this right, but it is proven to work. So we had a lot of battle stories where we had tiny little bugs which didn't work out at the beginning and was hard to find, but eventually we succeeded. The next thing is one puts a key value store on top of this Raft protocol, and the key value store will then basically fill the entries of the log by events. And thereby you have a consistent data store, key value store, which is resilient against failure. Let's try a short demonstration. So I have uploaded these slides, so they should be clickable. And if that works, oh, I need internet connection. Okay, I haven't set this up, so never mind. So the idea of a Raft is that we have 5 servers. One server first gets into a timeout, sends out the event that I want to be leader to all the other ones. And as soon as the majority says, oh, I accept you as the leader, he will be the new leader. Otherwise, the next server will try to get the leader until we have one leader. And during this process, no events will be able to be written. Eventually, we will end up with the leader. If we shut down the leader, one of the other ones will figure out, oh, the leader is gone. I will have to take over. And so on. So we always have one leader unless all of the servers are down. Something happened with my slides, sorry.
But didn't you have it localhost on your local machine?
Yeah, but I think it downloaded stuff from JavaScript libraries.
But the internet usually works here if you just
I could try. The thing is, I can't.
go to Netflix.
Yeah, just give me a minute. It will be.
You just select in the middle, it says network number.
There we go. Thanks. And hopefully that works in a minute.
Yeah.
Doesn't seem to load this one. Somehow it doesn't work. So never mind. Let's continue without the demonstration. So let's sorting. Next problem. So first of all, we now have solved that all servers can
Close the door.
agree on things. Next problem. Sorting. So the problem, data stores need indexes. Indexes typically are sorted. Could you please close the door? Could you please close the door?
Room is full.
Thanks.
We don't want to be kicked out. Just close the door.
So the problem, data stores need indexes. Indexes are sorted, so in practice we need to sort things. Not an unknown problem, but everything you learned probably at the university or at school about sorting algorithms are rubbish on most of the published algorithms that we have are rubbish on modern hardware. Because they are optimized on the number of comparisons you have to take, but none of them takes the modern hardware into account. Because the problem is no longer the comparison in computations, but the data movement. Because it is more expensive to load data from lower levels of memory caches than it is to do a couple of computations on high-level caches. So, since the time where Apple IIe was blazing fast hardware, which is a couple of years ago, the compute power in one core has increased by roughly 20,000%. A single memory access only by a factor of 40. And in addition, we have up to 32 or even more cores in a single CPU. So that means the computational power has outpaced the memory access by a factor of 1,280, roughly, even more. So that means we can do 1,200 operations more in our CPU for one data access in the same time than we could in the time when most of these algorithms actually were invented. So we need an ideal algorithm that can do parallel sorting and makes use of the amount of CPUs that we have, and that makes use of all the cache layers that we have in our main memory. And the only algorithm that really works there is a merge sort. So, idea for merge sort is I have blocks which are sorted. From the beginning, this block is exactly one element large, so sorted by definition, and then I just merge two of them and they are always sorted. In addition, I will take each sorted block, each of them, and put them into one min heap. A min heap is a structure, a balanced tree. So balanced tree means all these parcels have around the same length. Some of them may be a bit shorter. So most of them have the same length. And the only rule is the first element, so the root element, is larger than all elements attached to it. So all elements below are higher. And it is pretty easy to remove this top element from the structure and put one of the other guys on top, because then still the condition is true. And with this thing, I can actually put a couple of these min heaps for each of them together and just look on the top element to decide which one I have to pick. If I would do, let's say, a quicksort algorithm instead, I would pick one of these elements and then search through the entire block, which could be large, and put it on the left or the right hand side. With this structure, I always look at the top element, and the upper part of this tree is actually fitting into level 1 cache of a CPU, and a bit more fits into level 2 cache. That means I have super fast data access on the top of the tree. And thereby I can do a good sorting on a large data set. So with this algorithm, you can actually get all your 32 CPUs working on 100% utilization on sorting a huge data set, which is the desired solution to get fast sorting. Because nearly all comparisons hit level 1 or level 2 caches. Next problem. Log structured merge trees. So the problem is, people rightfully expect that a data store can do fast writes. So why should my data store be slower than writing to RAM? But at the same time should be able to hold more data than RAM. It should work well with SSDs or spinning disks, or whatever hardware I have. It should work. Should have these fast bulk inserts, so I have large data set and want to push it in as fast as possible. And of course, I want to have super fast reads. Especially if my hot set, so the majority of the data that I'm using in my application, fits into main memory. Why should my application be slower than this speed? Well, how can we do this? So traditional B-tree-based structures, like we have in relational databases, often fail to deliver the latest two. So bulk inserts, the B-tree structure actually has some drawbacks there when we try to insert a lot of data into different layers. And they don't provide super fast access if the main memory does, if the main or the hot set does not fit into main memory. How could we do that? So the solution is a so-called log structured merge tree. It's a several layered or level approach. So you can define how many levels I want to have. In the first level, we have like short blocks of data. All of them are sorted. But these are short enough to fit into the level 2 cache. Or into like level 3 cache, but not larger. So we can easily or fastly write to those things. And of course, they have to be sorted with the algorithm that I have presented before. As soon as we run out of these things, we need to do a compaction task. And a compaction task will take a couple of these blocks in level 0, merge them together into larger blocks, which are still sorted, and push them down on level 1. So level 1 is larger, but we know the large block is sorted. And as these fill up, we pull it down to level 2. Again, much larger, still sorted, and so on and so on and so on. However, this push down can happen in a background thread, so it doesn't block any ongoing work. Write can be done in level 0, so it's pretty fast because that is main memory. Mostly a bit backed up on disk, of course. And so thereby we have fast writes. We have a good compaction going down there. If we want to search something in here, logarithmic scale. However, in addition to these sorted blocks, we insert something which is called a Bloom filter, or the more modern version, a cuckoo filter. A cuckoo filter is a persisted data structure, which you can ask, I have a key in my hand, do you know if this key is stored in your block? And the thing should answer yes or no, but it is allowed to lie. But only in one certain case. So, if the Bloom filter says, no, I don't know this data set, then it is guaranteed that it is not inside this block. If it says yes, then it may not be in there. But this is not as bad as it sounds, because the thing is, if I need to find a certain data set, I will start at level 0, ask either search in here directly because we are in main memory, or ask the Bloom filter. And most likely only one of these things will say, yeah, probably need to scan my block because I may have the data. If you don't find it here, you just go down. And most of the time, only one of them will say, probably I have it. And then the further you go down, the lower the chances is because you increase the Bloom filter. However, if a data set is not stored at all, it's actually quite fast to find that out. Because all the Bloom filters, which are fast, will say, no, I don't know the data set.
How fast is it, the Bloom filter?
As far as I know, is constant time plus memory access. So because it's hash-based. But it doesn't have this logarithmic search, which you would have if you ask inside the data. And the next thing is, the Bloom filter is small enough to put into main memory, although this sorted list of documents may be like 2 terabytes long. So, summary. The first writes go into these mem tables, which is level 0. So in memory mapped files, most likely. All files are sorted. Oh, and I forgot. All of them are immutable. So as soon as I have pushed something down into level 1, it stays immutable. Thereby, I can super easily cache the Bloom filters, because the answer will never change. Merge sort can be used if I push them down. So we have a pretty fast algorithm to create the sorted set of the lower layers. All writes only have sequential I/O, because on level 1 or level 0, the mem tables are just append. Maybe I have to resort on pushing it down on level 1. And for the other ones, I always know, oh, I have the first element, the second element, the third element, and I actually know how large the file will be, because I know both blocks, how large they are. Then we have Bloom filters or cuckoo filters for fast reads. So we get a good write throughput, because we write to main memory, and reasonable read performance. Of course, these things will be slower than putting everything into main memory and having hash index on top of it. But they are made for the condition that your dataset is larger than your main memory. And as they are so good, they are used in a large amount of databases. So in Bigtable, Cassandra, HBase, Influx, LevelDB, Mongo, ArangoDB, RocksDB, SQLite, and MongoDB uses them via Tiger. So a lot of databases have this technique. Next problem. So the last two we had, sorting, log structured merge trees, were important for a single node. They were not for distribution. Now let's move back to distribution. Distribution, we have several machines. Each machine has its own clock. And with a probability close to 100%, those clocks are out of sync. So that means whenever we put a timestamp into our document and move it over to a different server, this different server will say, oh, this thing is kind of old, or it's in the future, which is bad. So we need a solution for this. And general relativity poses that we have those things. So documents in the future, and we don't know which is the exact order of incoming events. In practice, clock skew happens, so we have off a couple of milliseconds. So in theory, this is around 20, 30 milliseconds that we have in clock skew, even if we do all these network clock synchronization protocols. If you are Google, or you have the same amount of money, you can actually buy atomic clocks and put them in every of your machines. So you get that a little bit closer. This is the thing they did with Spanner. So then you can actually rely on the clock of the machine more or less. And the network time protocol helps to do like the arbitrary man hardware to get it down to 20 milliseconds. But still there is a clock skew.
Sorry.
Yes, please.
Even if my NTP
this server is local to my data center?
Yeah, there's a network delay between all your local servers. So it may be a bit smaller then, but still you will have clock skews. You're welcome. And of course, this thing is also designed for data center to data center replication and cross data center functionality. Works there as well. So, because of all the above mentioned problems, we cannot compare timestamp from different nodes. So you can compare the timestamp of the same node, but as soon as you try to compare timestamp from different nodes, you will end up with a broken ordering of things. Why would this help? Because in most cases, you actually want to have this real order of events, what happens one after the other. Assume two users updating the same document. Probably it's good to know who was the first one and who should get a conflict. If you have like master-master replication, write this here, write this there, it's unclear who was actually the first one. So for conflict resolution, for log sorting, or even for detection of network delays. So whenever you see, oh, there was a short network outage of a second, you could see that because the message was actually a bit delayed. Next thing that you often use in databases is so-called time to live. Easiest example is a session. So user logs in, and he should stay logged in for the next 2 hours, and if he doesn't do anything in the 2 hours, the dataset should go away. Hard to implement in a distributed system. So what is the idea for a solution? So every computer has a local clock. So it may not be accurate. There may be clock skews, but we have one. And we use NTP to synchronize, so we have like an upper bound of delay. So if two events on different machines are actually linked by causality, so that means I get an event in here, and because of this event I had to fire a different event on the other machine, then the cause should have a smaller timestamp than the effect. Basically, user request comes in, first timestamp, I write the document, second timestamp, and I send it out. Then the first timestamp should be smaller than the second timestamp. And the causality is a message is sent. So thereby we send a timestamp with every message. And then we have a hybrid logical clock, because it's a hybrid of a physical clock, the one that is attached to the computer, and a logical clock, which is just a number which adds on top of the physical clock. And the idea is that the hybrid logical clock can always return a value which is larger than the local clock and the largest timestamp you have ever seen. So that means if the other machine says, I'm already 5 minutes in the future, then the timestamp the logical clock will send out will be 5 minutes in the future in comparison to your local clock. And therefore I will just take, or the clock will just take the real timestamp of the messages it has seen, plus adds a small fraction, so that this timestamp is actually larger than the logical timestamp from the other machine. And eventually over time, the clocks will synchronize again, and thereby the local clock can actually catch up with the largest timestamp that I have seen. So there will be a small portion where it is off, but the hybrid logical clock actually fixes this. And then we have the guarantee that whenever I have two events that have a causal relation, then I have an ordering based to the hybrid logical clock approach. So causality is preserved, and we have time to catch up with the real time eventually. If you want to read more details, a blog post about this is written down below. So I have shared the slides, all the links will be available. Next topic. I think I'm good on time. 5 minutes, right? Yeah, that will work. So distributed asset transactions. Database world, ACID. first of all, atomic. Entire transaction either works entirely or not at all. Consistent. So I see a consistent state when I start my transaction, and if something happens in between by other users, I don't see this state. Isolated. So concurrent transactions don't see each other. And durable is whenever I crash, it's still there. So all of them are doable if the transactions happen one after the other, because then I can have an ordering and I can see what is ongoing. But we have more machines, so they are not one after the other. In a distributed system, we have to make sure that all nodes agree on whether the transaction has happened for atomicity. Because then I can ask, is this transaction that I see here done or not? How can I create a consistent snapshot across nodes for consistency? And how to hide ongoing activities until a commit for isolation? And how to handle if one of the nodes is lost for durability. We have to take replication, resilience, and failover into account, especially for the last point. What happens if my machine crashes and it said it has committed something? Then the failover machine should have committed as well. This is a whole topic for like a week of talks, how to implement that right. So, but with all the things that we have before, we can actually get pretty close to these guarantees. So we need something that agrees on the state on transactions. We use Raft. We use hybrid logical clock to get a timing ordering on all the transactions. Then we need failover. Of course, I won't go into details there. And the last thing I missed, isolation. This again is done via this agreement on the transactions. So we could either use the Raft for like everything that happens, works, but the thing is the Raft protocol is super slow. It is super consistent but super slow. So that means your database won't be scalable anymore. So we need to find some kind of hack around it. And we just need to agree on certain like snapshots or points in time which should be consistent. And then need to find something which gets away with all this stuff in between. And because this is so hard, I just created a list of which distributed databases do it and which don't. And most don't. So ArangoDB doesn't have distributed asset transactions yet. Bigtable, CouchDB, and Couchbase, DataStax, and so on. So actually most of the well-known databases don't have it. CockroachDB claims to have it. So I think they pretty much are there. I haven't used them in production yet. Google Spanner claims to have it because they use like Google's atomic clocks and don't have the issue with timings. And ArangoDB has a plan on how to do it, which is ongoing work right now. So sooner or later, we will remove ArangoDB from here and move over there. And very few of the distributed engines promise asset because it's so hard and so many things can go wrong. And you have to do the design for failure. So the basic idea, use multi-version concurrency control. So we can have multiple revisions and we just have to make sure who sees which revision. Writes and replication decentralized and distributed. So without them being visible because we haven't agreed them to be visible. Then we need some place where we can do the switching. And this place needs to be persistent, scaled out, replicated and resilient. And here we are actually by starting over here again, right? So we need a system that actually solves these issues to solve these issues. Never mind, this is a bit easier of a problem because we have more control over it. And you can reduce the amount of data that actually flows in there. So transaction visibility needs to be implemented with multi-versioncy concurrency control, and timestamps play a crucial role. Therefore, hybrid logical clocks. That's it. All the links. If you want to get into deeper details, I will be around for this day. We are an open source project, so if you like the talk and would like to support us, it's super important for us if you go to GitHub and click on please add a star, because that will help. Otherwise, I'm open for questions. Thank you very much.
Comment and a question, if you please. Is a comment, I do believe that Galera replication for MySQL and InnoDB cluster are doing distributed ECD transaction.
Yeah.
Question about the logical clock. Is there no risk for a cascading push of the clock into the future?
Yes, there is a small risk of it cascading into the future. However, in practice, they will catch up because of the NTP protocol. And I think we can push into the future with a couple of digits, I think 8 or so.
So NTP will push back?
It will push at some point, because there's the real timestamp and then you have this offset. And the offset can never overflow into the real timestamp. And then at some point you actually get the real timestamp.
Thank you.
Yes,
On
please.
the same topic, you said this gives you a reliable clock. Is that a pragmatic statement or is this mathematically correct?
So the question is if the hybrid logical clock gives you has a proof that it actually gives you a real clock which synchronizes this, and yes, it is proven, written in that blog post. So I can't sketch the proof right now, but yes, it's fundamentally proven. Yes, please.
The consensus algorithm you presented is not resilient against malicious attacks, right?
So the question is if the consensus algorithm is resilient against malicious attacks. I think the algorithm itself, not so really. So if you get into one of these players, I don't know. Yeah. So, but the thing is that this algorithm is not open to the public. It will be inside your own network behind a firewall. And if you are in there, then you probably have easier targets. Yes, please.
So lots of people don't get to ACID. What's your particular driver for wanting to have that?
Okay, yeah, I forgot to talk about this. So what's the driver to actually get a distributed system into ACID? And the thing is development experience. Because if you have ACID guarantees on the database, it's super easy, comparably, to write the application. If you don't have this ACID guarantees, that means you can end up with lost data. You have to make sure you write something, and maybe if you read it, it's not there. All these failover stuff you have to handle in your application. Then you may see non-isolated things, so gets kind of hard in the application then.
But from everything you said in this talk,
Yeah.
it's not easier to live with all of that than to implement ACID.
So the question is if it isn't easier to live with all that things in the application than it is for ACID. Probably yes, but it means shifting the work from your shoulders on our shoulders, which is pretty desirable for you. So it's all good.
Okay, last question. Because
Yeah.
otherwise
Yes. Oh, sorry. Yeah. So last question, please.
So you mentioned that only 2 databases that support distributed ACID.
Yeah.
Is it only open source databases, or you mentioned it's the whole world of many other commercial databases?
So the question is if those are the only 2 databases out there in the world. The answer is, I must admit, I don't know, because I haven't created this talk myself. And I would have to ask Max now if he only included open source or also commercial ones. Okay. So I don't know.
Spanner is not open source.
Right.
Cockroach.
I think Cockroach is. Yeah.
The foundation is Spanner. Okay, cool. Thanks a lot, everyone.
Thanks.
Good. Let's give a round for